Hi folks, we're looking at extreme values today using some more complicated functions. As we move to more complicated functions, some things to bear in mind are to be aware of the domain of your original function. If the domain, say, only includes positive numbers and you find a critical value of -3, well, you don't really care about that critical value. If it's hard to find critical values by looking at them just by inspection, then actually set up and solve an equation where f prime is equal to 0. Take the time you need to find those critical values. On a polynomial, they tend to be easy to find because you can just factor and look for them by inspection, but on other functions it may require more work. Also remember that critical values include those values that make the derivative undefined, so things that might cause division by 0 could be a critical value as well. Just as a refresher, critical values are x values that cause the derivative to be 0 or undefined. Let's take a look at that in the context of a more complicated function. In this first example, we're going to find intervals of increase and decrease and any extreme values on this function, y equals the natural logarithm of x minus 2x. So just like we said in the last slide, we want to check out the domain. This has a ln x in it, so its domain is x greater than 0. You can't take the natural logarithm of 0 or a negative number. You can only put in positive values into this. And that means if we find any critical values that are outside that domain, we really don't care about them. All right, let's differentiate. So we'd have dy by dx is ln x turns into 1 over x, 2x turns into 2. There we go. Now some of you may be able to look at that derivative and tell what number turns it into 0. What number zeroes this whole slope function out. But for the rest of us, we're probably looking at it and thinking, And if that's the case, then just set the derivative to equal 0 and hunt down that critical value. Okay, so right now we're hunting critical values. Now right away there is a critical value of 0 because it causes this derivative to be undefined, but we don't care about that critical value of 0 because it's outside of our domain. So right now I want to know what number is going to make this equation true. It's an equation that has fractions in it. I don't particularly love that, so maybe I will times both sides by x to get rid of those fractions. And what will I have? I'll still have 0 over here. I'll have 1 minus 2x. Okay, I can solve that. 2x equals 1. X equals a half. Would that really work? Yeah, 1 divided by a half is 2. Minus 2 would give us 0. So there's our critical value. Of a half makes slope 0. Now there was that other one that made slope undefined at 0. Slope undefined. But we don't care, okay, because it's outside the domain. So now all we know is that at x equals a half, there's going to be a slope of 0. We don't know whether there's a max there, a min there, or possibly neither. So that's where the number line comes in. And this time I'm not going to have my number line go all the way to the left because the domain is only 0 and greater. A half is the critical value, and I'm going to be subbing in here to 1 over x minus 2. So what's a number, I don't know, between 0 and a half? Let's think. Maybe we'd think of a quarter. So 1 over a quarter minus 2. If I subbed in a quarter for x. 1 over a quarter is 1 divided by a quarter, or 1 times 4. Really, that's just the number 4 minus 2. Hey-o, we get a positive number. That's what's going on the derivative. Now that means that from 0 to a half, the original function is increasing. if I put in a number bigger than a half? Well, let's just choose the easiest one. Put in 1 into this derivative. I'd have 1 minus 2. Oh, geez, that's definitely negative. So it's decreasing. So at a half, we change from increase to decrease, meaning there is a max at a half something. Now, to find the exact value of the y value, we'd have to go back to the original over here. And we can do that, no big deal. So the y value would be ln of a half minus 2 times a half, or ln half minus 1. Or if I wanted to, I could go to my calculator and figure that out. So ln of 0.5 minus 1 gives me negative 1.69. That should be our maximum on this function. We can say that it is increasing from 0 all the way up to a half, and that it is decreasing from a half until infinity. We can also show those in interval notation, but it's kind of nice like this too. So that's answering the question, intervals of increase, decrease, right here. And here's our extreme value. Let's head over to Desmos and just confirm that this is correct.
There's our graph, and as expected, we've got a maximum at 0.5, negative 1.69.
We know that our result is correct here. It was a little more of a pain to find the critical value in this non-polynomial function than it was, say, in the last lesson. But all we had to do was set the derivative equal to 0 to hunt it down. Now, we're going to do a couple more examples that involve more complicated functions at the end of the video. But before we do that, I want to touch on the one other sort of major topic in this video, which is finding absolute extrema on closed intervals.
So far, we've been dealing with functions on their entire domains, but there are times when we might only want to consider a small chunk of the domain. So, for example, if you're producing t-shirts on a small local level, it might not help to find out the profit is optimized if you make 3 million shirts. A restricted domain might be useful, say if your production is capped at 10,000. So if you have an interval, and a closed interval in particular, that means one that includes the endpoints, like this, then you can have absolute max or min at either the critical values, which would be here and here on this function, or at the endpoints. And we're talking about absolute extrema here. So the absolute min would be this point right here that I'm coloring in, and the absolute max would actually appear at the endpoint. If you want to test for an absolute max or min on an interval, you need to test the endpoints as well as the critical values. And since it's only a few points that you're going to be testing, it's probably overkill for us to make one of those sign diagrams and show where y prime is positive and negative. All you need to do is find the y value at each of the points that you're interested in, and then compare them to see which one is the highest and the lowest. Let's try that on a function.
Here's a question about absolute extrema that's on a closed interval. We're looking at this cubic, but only from x values from negative 2 to 4. And they're inclusive because of the square brackets here. So I want to know what are the important values to test. Obviously, the endpoints are going to be important. And aside from that, it's really the critical values as well. Let's find them. dy by dx, pretty easy. 3x squared minus 3. Let me factor them. And after you factor a bit, you can't help yourself, you gotta factor some more. So that's a difference of squares, x plus 1 and x minus 1. This one's going to give us a critical value of negative 1. This one will give us a critical value of 1. Those are our critical values. We could make a number line here and decide when it's increasing and when it's decreasing, but it still wouldn't spare us from having to test the y values at all the different points. So when you have a closed interval like this, the simplest thing to do is just find out which one of these x values is going to give you the highest and the lowest y value. Okay, so I care about the endpoint. I care about this critical value of -1. I care about this critical value of 1. And I care about the other endpoint. And I'm just wondering which one of these is going to give me the biggest and smallest y values. Let me just plug them in. If I put in -2 here, I'd have -2 cubed, which is -8, minus 3 times -2, which is +6, plus 2. I'll have a y value of 0. If I put in -1, I'll have -1 cubed, which is -1. 3 times -1 and minus gives us a +3 is 2. There we go. If I put in 1 into this, it's not so bad. 1 minus 3 plus 2 is 0. And if I put in 4, I would get 64 minus 12 plus 2, which is 54. I've done all this work to figure out what the y values are. Finding the absolute min and max should be really easy now. Right here, this is the lowest y value. It happens twice. So the absolute min is 0. And it happens at x equals -2 and x equals 1. It happens twice. The absolute max is just the biggest y value. And that's easy to find. It's right here, this 54. And it happens at x equals 4. So the actual value of the min or max is the y value. And sometimes we like to say where it happens as well. So if you've got a closed interval, just check the endpoints, check the critical values. You can make the sign diagram if you want, but it's not really going to get you a whole lot further ahead or spare you from having to check the actual y values.
Here's the graph of that cubic on the domain that's given from -2 to 4. And you can see that there's the lowest y value of 0. It occurs in 2 different places. And there's a highest y value over here of 54.
For the rest of this video, we'll just look at some more examples of finding extreme values on some sort of more complicated functions. But the technique is always the same. Take a look at the domain and then look for places that cause your derivative to either be undefined or 0. So here I've got a square root, x minus 2 root x plus 1. Right away, this part here, because it's under square root, I know that that has to be 0 or greater, which leads me to a domain of x greater than or equal to -1. So that if I find a critical value that's, say, -2, I can say, I don't care. All right, so let's rewrite this in exponential form. Or maybe at this point you've gotten some tricks for dealing with square roots. When I differentiate now, I'll have 1 minus 2. Let's see what happens. The half's going to come down front. I'll have x plus 1 now to the power of a half. Do I need the chain rule? I really should use it. Let's see, because I've got an inner part right here of x plus 1. Now it so happens that its derivative is 1, so if you miss it, you're probably okay. But that's through good luck as opposed to good judgment. Let's see what happens if we simplify this. So that's 1 minus 2 times a half is just 1. 1 minus x plus 1 to the negative a half. Or I can rewrite that in radical form. And again, maybe some of you see right off the bat the numbers that are going to zero this out or that are going to make it undefined. I can see that the number -1 will make this undefined. So it is a critical value, though it's at the boundary of the domain, so we wouldn't be considering anything to the left of it. So it's not going to be that important to us. If you can't see by inspection what number is going to zero this out, then we have to go ahead and actually hunt that critical value, and that is fine. I think I probably would on this one. So that means make the derivative 0 and see what the x value is. When I look at that function, I think, oh my, or that equation, I do not like those fractions. I like them even less than the square roots. So 0 times anything is still 0. Over here I'm going to have 1 times root x plus 1, so that's just root x plus 1. And here the fractions are going to go, so I'll just have -1. I can rearrange that to 1 equals root x plus 1. And this whole process is just around hunting down that critical value. I can square both sides, so I'll have 1 equals x plus 1, or x equals 0. That's our other critical value. And if I take a look at it over here, if I put in 0, I'll have 1 minus 1 over the square root of 1. Yeah, that'll give me 0. So the critical values that we found were -1 makes the whole thing undefined, and 0. Now when I go and make my number line to test what's happening, because that's what I'm going to do in this case, it's not a closed interval that we're given, I'm going to think about starts at -1, goes to 0, and those are the only important places in the life of this function. So if I pick a number between -1 and 0, say I pick -0.5, and I put it in this derivative over here, I'm not entirely sure what I'm going to get. I'd get 1 minus 1 over the square root of, if I put -0.5 here, I get square root of 0.5. Depending on how good you are with your mental math or your understanding of fractions, then you can probably determine that this is going to be negative. If not, then just head to your calculator and plug it in and see what values you get. I guarantee you will get a negative value here. Okay? Similarly, if I go and I put in a number bigger than 0, so, sorry, just to be clear, y prime is negative, so y is decreasing. If I put in a number bigger than 0, say I put in the number, I'm going to choose the number 3, because that's going to mean I can square root it easily. 1 minus 1 over the square root of 3 plus 1. That would be 1 minus 1/2. That's definitely positive. All this work to determine that we're going from decrease to increase, where we have a min at 0. And mercifully, 0 is pretty easy to put in the original function. So g of x is the same as y equals. If I put in 0, I'll have 0 minus 2 times the square root of 1, or -2. That's our analytic technique for finding this minimum. Let's check out whether it's the same on Desmos.
As expected, this graph has a minimum at 0, -2, right there. And you can see that its domain really is x is greater than or equal to -1.
We'll take a look at one last one to find extreme values on. So we have an exponential here. H of x is e to the 3x minus x. The domain on this function is not restricted at all. The only things that restrict domain are even roots, natural logarithms or logs with any base, or if we have division with an x in the bottom or variable in the bottom. So now we can go ahead and we can differentiate. Remember, this is an exponential with an inner part of 3x. So h prime of x is going to be e to the 3x times the derivative of the inner from chain rule minus 1. Now you can't go 3 minus 1 here. Order of operations, that 3 is stuck with the e to the 3x. On the other complicated examples we did, maybe you could pick out the critical value by inspection, but I think here it's going to be very difficult. So let's hunt down a critical value. And we do that just by setting the derivative to be 0. And we solve that equation by whatever means the equation type requires. So the weirdest thing in here is that it has e to the 3x. Let's try and isolate that. I'm going to divide by 3. There we go. Unfortunately, I've got this x stuck up here in the exponent. So the way to get it down is to take the natural log of both sides. And you could use log base 10 if you want. But here, since we're dealing with a base of e, it might be a little slicker just to do it with a natural log. So, do it to both sides. Ln of a third, ln of e to the 3x. And the great gift of logarithms is that you can bring your exponent down. So I have 3x ln e and ln of 1/3. Now, that really means ln of 1/3 equals 3x, because ln e is just 1. Or x is ln of 1/3 all divided by 3. And I think at this point I would go and grab my calculator and figure that number out to a bunch of significant figures. Where's my calculator? So I got roughly negative 0.366. That's my critical value. That's where there's a slope of 0. I don't know if it's a max, min, or neither. So let me make a number line. This time it's unrestricted to the right and left because the domain was fine. And I'm going to have to plug some numbers in to this derivative over here. So if I put in like -1, then what would I get? Well, I'd get 3 over e cubed. Maybe I want to actually do that in my calculator. If I put in -1. Here's what's going to happen though. If you put in a big negative number, then you'll get this thing gets flipped and it'll be a big number on the bottom. So this whole part here will get to be tiny with a big negative. And then you'll have tiny minus 1 is going to be negative. Or if you don't believe me, just grab your calculator and plug this in. I guarantee you it's going to give you a negative value. So that's what's going on the derivative, which means that the original function is decreasing. Looks like we might have a minimum. Depends what happens next. Okay, now we can plug in something that's bigger than negative 0.366. You might as well make it easy for yourself. Choose the easiest possible number. Choose 0. So that'll be 3 e to the 3 times 0 is just 0 minus 1. E to the 0 is just 1, so 3 minus 1 is 2, or most importantly, it is positive. We're increasing. So we've gone from decreasing to increasing. We must have found a minimum at negative 0.366. And then to find the y value, I'm going to have to put in that number, negative 0.366, in the original function. So I'll take a second and do that. I got 0.6995, positive. That's where I think the minimum is on this function. Unless I've done some algebraic goofs, it should be correct. Let's check on Desmos.
As expected, we end up with a minimum at negative 0.366 and 0.7.
At this point, we have a technique for finding max and min values. We'll set up that number line and test on the first derivative around our critical values. So hopefully you're ready to try those practice questions. When things get rough hunting down your critical values, actually set the derivative to equal 0, and then do whatever means are necessary to solve that type of equation. Good luck.